Hi folks, welcome to video 2 of Forces in One-Dimensional Motion for Year 9. This video is on Newton's 3 laws. Newton's 3 laws is essentially a very important thing in forces. Newton's first law, it simply says, if there's no resultant force acting on the body, then the velocity of the body will not change. So if I have a car here, for instance, and I don't know, I've got a thrust of 1000 newtons here, and I've got a drag of 1000 newtons. I think that arrow might be a little bit too big. That car will just be going at a constant velocity. So that is an example of a constant velocity. For something to stay at constant velocity, or for something to be stationary, it should have no unbalanced force, so the resultant force should be zero. Now Newton said, if the resultant force isn't zero, if you do have a resultant force, then there will be an acceleration. And you can figure out the acceleration using this equation here, where F, very important, F is the resultant force and m is the mass of the body. Now the other thing that you can be asked to find is, if you measure the acceleration and you measure the mass of the body, you can be asked to find what is the resultant force, in which case you just rearrange that equation and use the one at the bottom. F equals ma, a very, very famous equation. Okay, so if I was to give you an example of one of these questions, what is the resultant force acting on a car if it is accelerating at 2 meters per second squared and the mass of the car is 300 kilograms? Well, what is the resultant? So I just use F equals ma, and then F is just going to be equal to the mass, 300 times the acceleration multiplied by 2, which is equal to 600 newtons. Now, if it is accelerating in this direction, that means that 600 newtons must be acting in the same direction. So 600 newtons is in that direction there. The force and the acceleration are always in the same direction. The other type of question you can get asked is, what is the acceleration of the car below? So we can see we've got a force body diagram. First thing we have to do is find out the resultant force. The resultant force is equal to 150 newtons in this direction. So now we can find out the acceleration is just going to be equal to the force, the resultant force I should say, divided by the mass, which is equal to 150 divided by a mass of 300, which is equal to 0.5 in the unit of acceleration, meters per second squared, and it's going to be in this direction here because the acceleration has to be in the same direction as the resultant force. Okay, if the force remains the same for 4 seconds, draw a velocity time graph. Assume the car starts from rest. So I'm assuming these forces stay the same, so this force and this force stay the same for 4 seconds. That means the resultant force for 4 seconds will be this, which will mean the car will accelerate like this for 4 seconds. So if I'm asked to draw a velocity time graph, I know that the gradient of a velocity time graph is equal to the acceleration. So I have to draw a velocity time graph with a gradient of a half, i.e. every time I go over 1, I have to go up a half. So after 4 seconds, so after 1 second I'll be at a half, after 2 seconds I'll be at 1, after 4 seconds I should have speeded up to 2 meters per second squared. So this is how forces relate to what we've learned in the last topic about motion. Once you know the resultant force and the mass, you can figure out the acceleration. As soon as you can figure out the acceleration, you can draw the velocity time graph. And if I want to now, I could figure out how far that car has travelled in that time, because distance travelled is just equal to the area underneath the velocity time graph. Okay, what is the change in the car's velocity if the forces below act for 8 seconds? So, I've got an initial velocity of 20 meters a second, and I'm going to say that initial velocity is acting in this way. I should have wrote that down before. Okay, now the resultant force is going to be 300 newtons, but it's in this direction here. Okay, so because the velocity and the resultant force are in opposite directions, I'm going to say that the velocity is in the positive direction, so I'm going to make that force minus. Now I can get rid of this arrow, because I can see that because the velocity and the force have got opposite signs, I know they must be in opposite directions. And the question is, what is the change in the car's velocity if the forces below act for 8 seconds? Okay, so I need to figure out what the acceleration is going to be. The acceleration is simply the resultant force divided by the mass, which is minus 300 divided by 300. So the acceleration is going to be equal to minus 1 meter per second squared. Now, the car is originally going at 20 meters per second squared. If it accelerates like this for 8 seconds, well then the new velocity, or the final velocity, will be equal to 12 meters per second squared. Because every second the car is slowed down by 1 meter a second. Okay, Newton's third law. Very poorly understood law at times. I'd urge you to learn off this definition. If body A exerts a force on body B, then body B exerts an equal and opposite force on body A. Mathematically, that is done like this. So this is the force on A. So if this is A, that might be the force on A. If that's A. So if this is B, well then the force on B is the same size, so the same length of arrow, but it's in the opposite direction. That's what that minus sign indicates. Okay, the important thing to realise with Newton's third law is that although the forces are equal and opposite, this can result in different accelerations because the mass of the bodies, A and B, so here's body A and here's body B, might be different. Body A has got a mass of 300, body B has got a mass of 600. Okay, the other thing I want to stress about Newton's third law is that it's always two bodies. Body A has to exert a force on body B, and then body B will have a force exerted on it by body A. Otherwise, if it was always just on one body, equal and opposite forces would mean there would be no resultant force and nothing could ever move. Right, so in this question, the initial velocity of body A is 15 meters a second in that direction, and the initial velocity of body B is 30 meters a second in that direction. Again, I've got a problem. The directions of these speeds are in opposite directions. So what I'm going to do is I'm going to get rid of that arrow, and I'm going to make this minus. And now that indicates to me that the velocities are in opposite direction, because now I've indicated it with the signs. Okay, so body B exerts an average force of 12,000 newtons on body A. The collision lasts 1 second. What is the average acceleration of A and B during this time? And what are the new velocities? Okay, so I've got the situation summarised here. So let me see, the force was 12,000 newtons. Body B exerts an average force of 12,000 newtons on body A. So body A is going to experience that force of 12,000 newtons, and if body B is moving in this direction, this will be the direction of the force. He's going to experience that. But of course, if body B exerts that in A, well then, by Newton's third law, body A exerts a force of body B of the exact same size, so 12,000 newtons, but it's in the opposite direction. So it's heading in this direction. So let's see what happens to the accelerations here. The acceleration of car A is just going to be equal to F over m, which is just equal to the resultant force, which is 12,000 newtons divided by the mass of 300 kilograms, and that's going to give me, let me see, 40 meters per second squared. Wow, an unbelievable acceleration. And the acceleration of body B is just going to be equal to the force divided by the mass, which is equal to 12,000 divided by the mass, which is, body B has got a mass of 600, so that's going to generate an acceleration of 20 meters. per second squared. So, in the question, we said that the collision lasts for 1 second. So if the collision lasts for 1 second, that means the forces exist for 1 second. And that means the accelerations exist for 1 second. So, if car A had an initial velocity of 15 meters, I've been a little bit sloppy here with my signs. So, I've said the positive direction of the velocity is in this direction. That means that I have to use a negative thing for the force here, because the force, this force, is in this direction. It's in the opposite direction of the velocity, so I need to make that a minus, which makes that a minus, which makes that a minus. Now, let me see, I'm just going to make that a minus, because that velocity is in this direction, which is in the minus direction. It's in the opposite direction to this one, which is the plus direction. So this force is in the correct direction. So the acceleration of car A is going to be this, and the acceleration of car B is going to be this. They're accelerating in different directions because they've got different directional forces acting on them. Car A is going to accelerate, if it was originally going at 15 meters a second, if it's accelerated at 40 meters per second squared, that means its new speed, Vf, is equal to 25 meters per second, and this one here, Vf, equals, well, this was originally going at minus 30, but now it accelerates at plus 20, so, and for 1 second, which would mean its new velocity will be 10 meters per second. So